I'm going to talk about some aspect of post-quantum cryptography. Namely, I'm going to explore the question, under which circumstances can classical cryptographic constructions be secure in a quantum setting? So the cryptography is classical, but the adversary is quantum. Of course, you all know if I use something like RSA or something like this, the adversary can factor and everything will be broken. But that is not my point here. I will assume that we don't use any assumptions like hardness of factoring or something like this, which do not hold in the quantum setting. I assume all our assumptions are perfectly quantum hard. But as I will tell you, there still is the surprising fact that even if all our assumptions are quantum hard, existing classical constructions may fail to be quantum secure. Actually, everything I tell you even holds in a setting where I don't assume any computational hardness, and still there is a gap. So before I come to the quantum problems, I will very quickly recapitulate the classical background of what I'm going to talk about, because I don't think there are many classical cryptographers in the audience here. So the object of study is a so-called zero-knowledge proof. Actually, the result applies to various different constructions, but I'm picking one of them to illustrate. So what is a zero-knowledge proof? Or, well, there's a certain issue in this talk. I'm going to simplify. I'm going to say only zero-knowledge proof. Those who know about these things, please replace that by zero-knowledge proof of knowledge, because then everything I say will make real sense. But those who don't understand what this difference is, for them it doesn't really make a difference. So what is a zero-knowledge proof? A zero-knowledge proof is some protocol where the prover plugs in some statement he wants to prove and some witness, so a proof of that fact. And out comes a proof. But it's a specific kind of proof. It's an interactive proof. So it's a number of messages being exchanged forwards and backwards between the prover and the verifier that convinces the verifier that this statement is true. And we have two properties. First property is the proof leaks nothing about the witness. And second property, it is hard to prove statements without having a witness. I mean, this makes it a proof. Yeah, what is this weird construction useful for? Well, there are quite a lot of, it occurs all the time in cryptography. So you use it very often to prove your honest behavior. So I send, for example, send a ciphertext, and I need to prove that this is a ciphertext of a well-formed message, for example. Yeah, you couldn't do that. Statement is this is a ciphertext of a well-formed message, and witness is, for example, the decryption key, because using the decryption key you can check that. Also, zero-knowledge is important because it is kind of a Drosophila of cryptography. So a lot of things that happen in more complex settings in cryptography, you run into the problems that you have in a purer case in zero-knowledge proofs. So studying the problems there tells us what we have to expect later. Okay, so if we want efficient zero-knowledge proofs, we very often use a particular form of zero-knowledge proof, so-called sigma protocols. Sigma protocols are zero-knowledge proofs which have three messages. So the prover sends one message. It's called a commitment. It has nothing to do with like bit commitments, it's just called that way. Then the verifier answers with a certain challenge, and the prover responds to that challenge. And it is constructed in a way that this interaction will not leak any information to the verifier, but we have the crucial property, which is called special soundness, that if we get two different valid responses, like two interactions, well, actually with the same commitment, different challenges, and then the two corresponding responses, this allows us to compute the witness. And as I will explain to you in the next slide, this fact implies that the prover can never make this proof without knowing the witness. Now the thing is, if you we will need this very often, so I copied it here, the important definitions on the whiteboard. So this is the structure of a Sigma protocol with the names of the messages. And here is the definition of special soundness repeated. Oops. Okay, so why does special soundness imply soundness? So why does it imply that the prover cannot succeed in a proof without knowing the witness? And we prove this by using a so-called rewinding. At least in the classical setting, this is what we do. So assume we have a prover, and we want to show that he cannot execute the protocol successfully without knowing the witness. So what we do is assume this prover can successfully answer to the challenge with a valid response. And then what we do is rerun it with one challenge, and then we reset it to the state it had just after sending the commitment. So we make a snapshot of the state and let her go back, and then we send a different challenge and get a different response. So we get two different responses, and the special soundness property, this one, implies that from two different responses, we do get the witness. So what we have shown is if a prover can complete the interaction, this prover could, in a different interaction, also produce the witness. So it means the prover knows the witness. So we have, in the classical setting, special soundness implies soundness. So implies you can't cheat as a prover. There's also the zero knowledge property that this doesn't leak anything, but that's not important for this talk, so we just assume this works out. Okay, so this is all we need to know about classical cryptography. I don't have the time to give you an example of such a protocol, unfortunately, but they are pretty easy ones, and they can be pretty efficient. But what happens if we go to the quantum setting? The classical security was easy, but if the adversary has a quantum computer, things are not that easy anymore. Because if we go back, this rewinding here is a tricky thing, because you can't just make a copy of the state and then continue from that state again. You can't copy the state of the adversary because it's a quantum state, so it's tricky to go back. And, well, I should first say, for specific cases of these protocols, we have a result that you can actually do this rewinding, namely if the response is uniquely determined by commitment and challenge. But the question is, does it work in general? Are the classically secure Sigma protocols also quantumly secure? And this is not a question about whether the underlying hardness assumptions also are secure. It's a question because there are Sigma protocols for which we don't use any that are information theoretically secure, and still the question arises whether we can do this rewinding. And the main result that I want to tell you is actually an impossibility. So I'm going to show, or sketch very roughly, that there is a Sigma protocol, a highly constructed one, that has special soundness, so it has this property that classically is enough, but that is not sound. So meaning the prover can succeed in this protocol even if he has no clue about the witness. There's a caveat. This is relative to some oracle. So I'm constructing a specific oracle, and only relative to that oracle I can prove the existence of such a Sigma protocol. But I personally believe that there is some chance that similar constructions exist without using an oracle, but I will not try to convince you of that in this talk because that would go into too much detail. But you can talk to me later about it. So what does this impossibility result? What does this impossibility result imply? Namely, it implies that a classically secure Sigma protocol may be quantumly insecure. Yeah, and everything, see the terms of condition for oracle separations, because it's relative to an oracle that possibly does not exist in the real world. Okay, how? Well, I have also copied down the impossibility result here if you want to look at it. And in order to prove this separation, or this impossibility, we use something that I call the pick one trick. And this is a technique that may be useful also in other cases, but so let me show it to you in general first, and then I will tell you what it has to do with our oracle separations. So the pick one trick is the following. So assume you're given a set S of some values. Yeah, let's say bit strings. Then you can encode this set S in some particular way as a quantum state psi that encodes this set S in such a way that for any other set P of the right size, yeah, there are some constraints on the sizes here, but I'm not going to list them. So you have some other set P, and it is possible to find some value in the intersection between S and P. So if I give you the state psi and some additional stuff, then you can pick one value in S subject to a certain constraint. So you could say, I want a bit string in S that ends in 0, 0. Yeah? Then you would make the set of all strings that end in 0, 0, and you would pick something from the intersection. So this is something you can do. Sorry? Yeah, actually, I need that it's pretty big. Yeah, so there are constraints on the sizes here, which imply that it's not empty. And there's another thing, and that makes it interesting. It is what I give you, this psi and some some unitary transformation, are not enough. You cannot pick two values out of this set S. Yeah, so you get one value, even one value that has a particular property, but not two. Yeah? Without this line, it would be trivial. I could just give you psi as the superposition of everything. You would measure it. You get one value from S, but not a second one. But this thing is actually the tricky one. You can search for a particular value with a particular property, but you cannot get two of them. And I have also written down this stuff here for your reference, because now I'm going to sketch how this pick one trick works. Yeah, you cannot get two. And there are some constraints about the lengths. So how do we do this? Let me first show to you how we can get this property that we can find an x1 with a certain property. So let's have a look at Grover's algorithm. Very high-level look, just recapitulate a few things. So the first step in Grover's algorithm is we create a state psi that is the superposition of all bit strings. That's the first step in Grover. You take the all 0, you apply a lot of Hardness. And then you repeatedly apply various gates. And one of these gates is the phase flip along this state psi. So it's I minus 2 psi psi. And you do some other things, like a phase flip depending on the predicate you're searching for and so on. But that's not so interesting here. And if you run Grover's algorithm, what you get is a value x that is in a set P which you wanted. Yeah? So that is what Grover does. It searches for, it finds you some value in P using operations like this. And now let's slightly modify this. Actually, the only thing is that the state psi is now defined differently. It's the superposition of all x in S. And then, of course, this operator is also defined differently. And now, essentially, you have just changed the space of all states to be not all bit strings, but all bit strings in S. So in the end, using the same analysis as you do in Grover usually, you get that X is in the intersection of P and S. And that was what the first thing of the pick one trick said. Now, of course, the question is, if we are given this state psi, and if we have somehow access to this unitary, perhaps we can somehow get two values from S. And actually, if the set S has only polynomial size, I think you can, or if P, well, under some conditions, it's even possible. But with the right size constraints, namely that actually the size of P must be a small fraction, but it must not know of S. Well, whatever. There are some conditions in the theorem. I don't recall them right now. But we can prove that it's hard to find two values of S, even if you have an oracle that allows you to compute this thing, and while assuming that S is a randomly chosen set of the right size. I'm not going to tell you how this is proven, because that's rather complicated, and for the second reason that I don't fully understand it. It is proven using unbiased adversary method, for those who know it, and involves a lot of representation theory. This much I understood.
Is it the prover that's finding the X1?
Sorry?
Is it the prover that's finding the X1?
Actually, yeah, when we will use it, the prover will be doing the X1 finding, and the adversary will be not doing this. Okay, so just trust me, it can be somehow proven. So how do we use this pick one trick? Because remember, we wanted to construct this impossibility result, that there is a sigma protocol that has special soundness, but is not sound. So what we do is we construct a set. Let's just draw everything. Yeah, there was too much. So we use the same pick one trick. This is just repeated what we had before. But we use now a specific set S and a specific set P. So in a sigma protocol execution, let's assume the commitment that we have sent is already we are after that step. Yeah? There are some subtleties there, but I don't have time to go into that. So assume we are after this step, and we are looking at this, we get a challenge, and we send a response. So we define now our protocol in such a way that in order to succeed in the interaction, given a particular challenge, you need to send a response so that the pair challenge response is in this random set of bit strings. And this random set of bit strings, so essentially in the beginning we pick a very large set of pairs of challenges and responses, but not so large that it's easy to find something in there if you just check random bit strings, you will find nothing, but there are still exponentially many such pairs, challenge and response. So this is the set, and the sigma protocol is defined that the verifier accepts if, given his challenge, I answer with a response that is in this set S. And now we give to the prover not an explicit description of the set S, but this quantum state psi. So this all happens somehow in the commitment, so we make sure that you can pick the commitment together with generating the state psi for some set, but I'm going to skip that. So we are after the step, and the adversary has the state psi, or the prover, the honest prover now has the state psi for such a set S. And this state allows him to find one value in a set P of his choosing. What set P do we use? Well, we need to find a challenge-response pair where the challenge is what is given by the verifier. So we define P as the set of all pairs of bit strings challenge-response where challenge is the challenge we want. And the intersection means it's an accepting challenge-response pair with the challenge we wanted. So whatever the verifier sends, we can do this thing and give an answer that he accepts. So we will always win.
What is the challenge?
Sorry?
What is a challenge?
What is a challenge? It's just the name for the message that sends. It's a bit string of a certain length. Actually, logarithmic length in this particular case.
But whether it's the P or the S, or what is it here?
Well, the challenge is just the name of this message, and the S is just a set that tells us for which challenge which responses would be valid. Not good? Okay. Yeah, so let me say this quickly again. We define a set S which has a lot of pairs challenge response. The task of the adversary is to manage for a given challenge to give the response that matches a response so that challenge response is in this set S. That is his task. And he solves this task by defining this predicate P that checks whether the first challenge is the one he wants. Then he does the search thing, and what he gets is a challenge response pair in S with the challenge that the verifier wanted. And by definition of the sigma protocol, anything in here is a valid interaction. Okay, I need to rush because I'm over time. So the prover can do that. He can always succeed in the interaction, but he cannot find two values in S. So we can give him an oracle that gives we can make sure that he gets a witness. So he will get, by special soundness, a witness if he has values x1 and x2, but this will never happen. So he cannot, no one can produce the witness, but the adversary can always succeed. And this gives us the impossibility result. And the oracle comes from the fact that we somehow need to encode all these things in a way that is accessible. Yeah, but with extra conditions, you can have successes. I'm not going to tell about that. We have a lot of other results using the same techniques. There are a lot of open questions, but there's a lot of not existing time. So I end my talk now.
You mentioned at some point that if there's a unique response per commit challenge pair, then the classical security results extend. So in your case, so do your bounds suggest, that a certain number of possible responses is necessary or sufficient? Or
so the thing is that one thing, in order to be able to do the Grover, the number of challenges has to be polynomial, but also the size of this set S needs to be super polynomial from the bounds from the hardness result, and this implies for each challenge there is a super polynomial number of responses.
Super polynomial.
Yeah.
You show this as basically the difference between the classical and quantum cryptography. It seems to me that it's more a difference between the computational security and information theoretic security.
It's in a sense, it's a difference between the computational classical and the computational quantum security.
And you showed that there exists a Sigma protocol, a classical Sigma protocol, which is not quantumly Sigma protocol.
Yeah.
But do you think that the set of languages that have classical Sigma protocols is different than the set of languages that would have a quantum Sigma protocol?
No, because under suitable assumptions you have well, at least if you give me quantum one-way, injective quantum one-way function, we don't have a candidate, but let's assume we have them, then I can give you Sigma protocols for all of NP. But the question is, can we use the same constructions? Because that construction is very generic, very inefficient, but they are like very efficient Sigma protocols, and those suddenly are insecure.